let's start our second afternoon session, and let's start the second morning session. And first we will start the announcement, which will give us Michael Douglas, please.
Thanks. Before I give my talk, I'd like to discuss very briefly a question involving postdoc hiring. To keep it brief, if you have questions, I ask that you come to me in private anytime during the meeting, and look at the website, which you can see the address up here for more discussion. So as you all know, we have been fortunate to be able to hire many postdocs in our field, and the decisions as to hiring and so forth and policy are largely made, almost entirely made by individual institutions, and that system generally has worked well. But there are some potential problems, and a potential problem which seems to many of us to be becoming a real problem in the last year is the problem of deadlines creeping forward into December, late November. We've heard cases. There are some cases in which these are due to external constraints, such as funding agencies, but there are many other cases, and a lot of confusion has been caused by it. So a number of us have gotten together and decided that the reasonable solution, which is actually adopted in several other fields, is to have a common deadline for postdoc positions, or at least a common earliest deadline. One is free to make later deadlines. And in this letter, we state our reasons and the deadline January 7th as our proposal. So this is signed, this letter is available, it's public, and it's been signed by a group of well-known institutions around the world. Again, you can look at the website, and we, after some discussion involving many more institutions, have reached this common January 7th reached agreement on this. So what we would ask, we would hope that the people we've spoken to have been very enthusiastic, and if you and your institution agree, you can also sign this letter by sending an email to postdocagreement@physicsrutgers.edu as described on the web page. And again, if you want more details of what this means in practice, I invite you to read this in the frequently asked questions section. So that's all I want to say. We're hoping that this will reach consensus and that it will solve a problem which has started to bother many of us. So with that, let me stop. And I asked for another introduction for my real talk, since I don't want to confuse the thing.
Okay, thank you for announcement. And now Mike will give us a talk. The title is Exploring the Hler Potential. Please, 25 minutes.
Right. So, okay, I'm a physicist again. So the work I'm discussing with the various students and postdocs at Rutgers has been a variety of works intended to address a relatively unexplored. So this project of deriving low energy theories from string theory, effective theories from high energy Yang-Mills theory and so forth, has gone very far. But as you all know, the greatest success has been for supersymmetric vacua, and increasingly less success for non-supersymmetric vacua, and even for the supersymmetric case, less success for the Hler potential. So we can take this prototypical example of the pure n=1 super Yang-Mills. We have this very nice ansatz for a solution for the superpotential, the Veneziano-Yankelevich superpotential. It's been much studied, confirmed, re-derived in many ways, describes the vacuum structure very simply. There are many, many generalizations. For example, the Dijkgraaf-Waffe prescription handles a very large class of n=1 models and produces the superpotential as a matrix integral. And the flux superpotential is, of course, another very broad ansatz that handles a large, not the whole problem, but a large class of interesting superpotentials in string compactification. But of course, the Kähler potential not being holomorphic is a more difficult problem. So why do we need it? Well, to review, we need it to get normalized couplings and masses. If we ever got far enough to believe a particular model was our candidate for our standard model, we might like to check the actual particle masses. And of course, at that point, you need this. Even before you get there, of course, basic quantities in a theory with broken supersymmetry, such as the scale of supersymmetry breaking, the definition of potential, depend on the Kähler potential. The whole problem of finding vacua in supergravity actually depends in an essential way on the Kähler potential due to this covariant derivative appearing in the condition dw equals 0 contains the Kähler potential. So those are very concrete reasons. And then more generally, if one wants to get a picture of the landscape, it's really true that the metric on the configuration space and distances are really just as important qualitatively as a potential function. And so there are various physical applications of that. It's well known that the metric appears in an essential way in the standard predictions of inflation. And some of the interesting constraints are phrased directly in terms of it. For example, the life bound that relates the ratio of tensor to scalar perturbations to a distance measured in the metric that comes from the Kähler potential. I believe Rana Kailash will speak more about these types of questions here. The volume of a region of configuration space defined in this metric is a good estimate for the number of vacua that a generic potential would have. It might enter a measure factor coming from inflation. There are various applications. Okay, so what do we actually know about this metric in general? Well, if we have a weakly coupled field theory, then of course it's the bare metric plus small corrections, and the normalizability tells us that we have to start with a canonical metric at high energy. So that's pretty strong, but obviously not the general case. Most of the really concrete work in the literature is based on the n equals 2 supersymmetric case, where the metric on vector multiple moduli space is determined by a holomorphic prepotential, as will be familiar to all of you. And the basic example, of course, is the U1 n equals 2 gauge theory, where besides the bare term, there's a one-loop correction that is related to the beta function and produces a non-trivial metric. So this arises, of course, in numerous situations in string theory. And a basic example would be type 2 on Calabi-Yau 2b with a conifold singularity. So I should say a deformed conifold with a 3-cycle. Rap D3s provide a charge multiplet under the U1 of that compactification. Okay, so let's go on to a simple example that we ran across. We were originally searching for low-scale models of supersymmetry breaking. So there is a lot of, again, powerful technology that goes beyond this superpotential in the case of local models, and especially gauge gravity duality. So that's where we'll eventually head. So one nice way to get the super-Yang-Mills theory is to wrap D5 branes on the S2 of a resolved conifold in the 2b theory. And again, there are simple arguments that this leads to n supersymmetric vacua and geometric duals for this. Okay, so now you might try to break supersymmetry by putting anti-D5 branes. Now, if you're really in n equals 2, the difference between brane, anti-brane is just a choice of n equals 1 within the n equals 2. So this is really the same theory, which is preserved a different n equals 1 subalgebra. But now, if we combine branes and anti-branes, or if we combine the theory that breaks preserving a certain n equals 1 in the bulk, such as an orientifold, and then wrap the anti-branes corresponding to that n equals 1, in other words, branes preserving the other n equals 1 on a cycle, then of course that should break supersymmetry by the conflict between these. Okay, so now there's a simple guess as to how the flux dual for this should work, which we learned from the work of Aganacic et al. About a year ago, that since you're looking at anti-branes instead of branes. Anti-branes are like negative branes, so let's take the ansatz for branes and flip the sign of the flux. So we take minus n in the Veneziano-Yankelevich superpotential. Okay, so formally, you've just flipped the sign and you formally have the same supersymmetric vacua, but these are often, very large S where you don't actually trust this in any string theory realization. And so where you're looking for vacua at small s, and lo and behold, you find interesting supersymmetry breaking vacua, so critical points of V that do not have dw0. You can take the rigid limit, so the D covariant is usefully approximated by del. And there are supersymmetric breaking minima at exponentially small s. Okay, so that scale S is low, but now we wanted low scale breaking according to the standard definitions, and so we went on to calculate the norm of the F term from the previous slide, GSS inverse SS squared. And it turns out if you do this, the cancellation in dW that happened, made it 0 in the supersymmetric case is replaced by a sum here. And of course, the supersymmetry is broken. F shouldn't be 0, and it's non-zero, but you find that it's order 1, and the supersymmetry breaking scale is a high scale, despite the exponentially small value of S. Okay, and then the supergravity corrections like e to the k actually don't affect this result. And this is the correct result. This is the tension of n anti-d5 branes. There's nothing wrong with this result. So it's good, but again, from our point of view of looking from low-scale breaking, we were led to wonder, since many people had said, consider anti-d5 branes down in the throat. Shouldn't they give low-scale breaking? Well, of course, qualitatively, the reason one expects low-scale breaking, despite this anti-brain tension, is the effect of the warp factor, that down in the throat there is a large warp factor that warps all the energy scales down. And so what was a large brain tension becomes a small brain tension in the rescaled four-dimensional units. And so we have to somehow put that in. Now, technically, there is, in the large volume limit, if you strictly take large volume before everything else, this effect goes away. Fluxes are quantized in units of alpha prime, and base force to warp factor, and this goes away. But there's a sort of order of limits, which we're just a different order of limits where we may look at the local limit. The rest of the volume can be large, but now we're going so far down in the throat that the warp factor dominates. Okay, so this type of question has been much studied, and there's a nice ansatz for the effect of warping on the Kähler potential. So one can argue that one has the same superpotential, Melanie Becker reviewed a bit of that, but that the Kähler potential is modified by putting an explicit dependence on the warp factor under the integral. So this is the warped metric, and this is Kaluza-Klein reduction and so forth. But a simple argument for this is that this really is a warped volume form, and to the extent that you're integrating here to produce the volume form, this is a natural replacement for it. Okay, so now one can wonder about this claim. So there are very basic things which are not obvious here. Even the question of should you trust, should you have a spontaneously broken n equals 1 is not totally obvious. So an example of something which is less obvious is that if you compare the metric on moduli space, which you can just compute independently, with the two derivatives on this expression, there are what appear to be correction terms that could spoil that relation, in which case you certainly would not have n equals 1 supersymmetry. Okay, so we wanted to understand an example in detail, and fortunately for the case of the conifold, there really is exact solution with fluxes and warp factor of the region around the conifold found by Klebanov and Strassler. Now, it's somewhat complicated, but fortunately these were strong guys and they worked it out. And so one point which is easy to see is, yes, indeed, except for the actual fluxes, everything depends on the square of n. So flipping n to minus n certainly does give a new solution respecting the other n equals 1, as we were assuming. Okay, so now what you want to do is you want to just compute the supersymmetry breaking, the fact that there is a Goldstino coming from the component of the S field because it's F breaking, and compute the coupling to the Goldstino. And indeed, you can go through, it's complicated, and see the warp factor suppression in that calculation. So now you can ask, well, is this an essentially 10-dimensional thing, or can you see it in 4 dimensions? Okay, so here is the 2-1 form that corresponds to the S field. So this is the underlying source of this modulus, the possibility of deforming the complex structure. And now we can plug it into the formula for the warped metric with the warp factor, since we know the warp factor from Klebanov and Strassler. And we'll do this in a second, but in fact you can see that this is going to reproduce, doing this calculation is going to reproduce the standard formula for M3 half squared. So if the story is just this, then yes, you should be able to see this in 4-dimensional effective theory. Okay, so to some extent we have resolved our qualms that I began with about 4-dimensional effective theory. You can show that this is true. Now, we have not resolved all of our qualms, okay? And I'm going to proceed on the basis of the formulas that I wrote before, but I don't know at this point. We are trying to do the full Kaluza-Klein reduction, but what I do strongly believe is that this is qualitatively correct. The warp factor does appear in this expression. Other terms that might appear also have this warp factor suppression. So let's go with this one. Okay, so there is a superpotential appropriate to an imaginary anti-self-dual background, the one that we talked about below. There is the warp Taylor potential and the corresponding metric. And now you plug in, and the warp factor becomes large in the throw whenever r to the 4 are the standard variables. And so it is true that this component of the metric is dominated by the throw, and you just have an integral to do. And here it is. This is the standard conifold term for the metric, and there's a correction coming from the throat region, which actually grows as S goes to 0. And it's really quite different than what one gets in standard special geometry. You can prove that these things are always finite. Volumes are always finite in standard special geometry, and it dominates the limit S goes to 0. And it's actually something which has a simple intuitive explanation. As I argued, the Taylor potential, according to the existing work, is basically the log of the warp volume. So if you just put the warp factor in the calculation of the volume of the throat, you find a term that looks like r squared. So it's the 1/3 power of the volume, and then indeed such a term in the Taylor potential produces such a term in the metric. Now what's very amusing, and we are not quite sure what to make of it, is that if you go back to Veneziano and Yakelevich, who studied super Yang-Mills theory from the gauge theory point of view, this was their ansatz for the Taylor potential. And it's a very simple argument, which is that S in the Baire theory had dimension 3. It's a gaugino bilinear, and you try to write something with the canonical dimension in terms of such a field, and this is the natural ansatz. Now, of course, this is a low energy quantity. This is a strongly coupled theory. It gets large corrections, and one cannot trust that argument, but it's quite amusing that in the strong coupling limit where we can trust the argument. So at this point one might ask, what about large curvatures, everything else? It's a fact about the Klebanov-Strassler solution that in this limit the curvatures stay bounded. They're just controlled by GS. The S doesn't enter. Okay, so now we plug this in and find the scale of supersymmetry breaking, and the inverse metric, the inverse of this factor here, is S to the 4/3. S is exponentially small, and that's what's responsible for the exponentially small scale of supersymmetry breaking. And that's exactly coming from the warp factor, as many people had proposed. It's interesting if you look at the details, it really isn't this inverse metric. The e to the k is a correction, but not the major effect. Okay, so now if you try to proceed to use this in a model, you find that just with a potential like this, of course, you have positive energy proportional to a power of S. It'll just roll down to S equals 0. Okay, so now you can find in the larger framework of a string compactification bulk effects that fight this. For example, the B cycle flux produces another term that you can push you away from 0. So we believe this can be realized in realistic compact models. We would not claim to have an example, but you do not need strong constraints on the parameters. It's a matter of searching for examples. But we found it's already quite interesting to understand the physics of warping through the Taylor potential, and we're trying to understand this better, as I said. Now, my other topic, since again this is local analysis, it's a fairly special case, is to try to talk about other hler potentials, and in particular, what about the open string sector? What about this original problem of computing the masses of the particles? What about the heterotic string? Okay, well, there's been very little work on this. Okay, so let's look at the original problem. It's 20 years old. What's the hler potential for the two cases? Again, we know for some subset of the moduli they see special geometry. But what about the rest of them? What if we take a 0-2 compactification? Okay, well, it's mathematically a well-posed problem in the supergravity limit. Of course, there will be corrections, but if you can't do it in the supergravity limit, you're probably not well positioned to think about the corrections. So let's think about the supergravity limit. In that limit, this is basically the natural metric on the moduli space of Hermitian-Yang-Mills connections, and that's just what you would think. You integrate variations of the connection against each other using the metric. Okay, and so all that is a well-posed mathematical problem, but obviously not a very easy one in this case of n=1 supersymmetry. And of course, it's hard to even get started because this assumes that you know the hler form for the Ricci flat metric, and while we know it exists, we don't have closed form expression for it except in trivial cases. Okay, and so one might then go on to think, well, this is the hard way. There must be some easy way. This is not how we did it for the closed string. We did not compute the metric deformations and integrate them against each other. We thought more deeply about the problem and discovered the structure of special geometry and these relations to algebraic geometry. And so let's try to duplicate that. Let's look for open string special geometry. And it's very likely that such a thing exists and plays the counterpart role in mirror symmetry that the closed string special geometry plays in controlling the re-expansion of B model quantities in terms of instantons. And so that's a very interesting project on which there's been progress, but already from the existing discussions such as BCOV, they suggest that these do not determine the open string moduli space metric, and there's no good reason to think that this is any easier. Suppose you could push this through and get some sort of differential equation, which this does not suggest. Why should that be any easier than this? This is a differential equation. You just plug in the metric, Rij = 0. Perfectly good differential equation, and we can't solve it explicitly. And all the other brane problems in a brane model are related by T-duality in some broad sense to this one, so why should they be any easier? So it seems like we have to be able to work to at least to some level of approximation with the Ricci flat metric, not just in the non-compact case, which I cited, but also to some extent in the compact case. We may not need exact or very precise answers, but at least something to get a qualitative picture. And so how do we do that? Okay, so we can try to write down simple ansatz. So the simplest ansatz, you can define a quintic in CP4 as a solution of one quintic equation in CP4. Now you can just take the trivial metric, the usual round, Fubini-Studi metric on the CP4 and restrict it to the quintic. Well, how far away is that? Maybe that's already good enough. Well, no, it's not very good. You can check it. Okay, so what can we try next? Well, maybe we can do better by taking the same form but adjusting the coefficients. That at least gives us more freedom to play with, and we might find a better one. And once you start playing this game, of course, you could start writing more general ansatzes for the hler potential with more coefficients. This is for a certain choice of C twice this one, but now we have 15 squared coefficients to play with and so forth. And so now we could try to find parameter values that give us a good enough approximation to the Ricci flat metric. Okay, so now there's a problem. Okay, you can try to go in this direction, but as string theorists, you kind of smell already that this is not a good idea because anything you can do at this point seems very arbitrary. It's not that computers are bad. It's that now when you say, what does it mean to be close to or if it Ricci flat metric, you're putting some arbitrariness into the problem, and there doesn't seem to be a natural choice. So how are you going? How is she going to learn by doing this? Okay, well, there turns out to be a nice natural choice, which has been used by the mathematicians for some years, called the balanced metric, and it's a little hard to explain. The actual equation defining it is fairly simple. So these S's are the whatever power of Z. So in this particular case, they are all the order 2, binomials in Z. They might be higher powers of Z for a better approximation. So we list all of those, and given the coefficient C, we form all of these integrals over the manifold depending on a choice of basis element I and basis element J bar. We come up with a matrix, and we ask that when we invert that matrix, we reproduce the original matrix. Okay, so this is a well-defined prescription. And what's even better is that this suggests a fixed point procedure. You just compute this, invert it, plug it back in, and keep doing this. And Donaldson shows that this converges. So this is actually fairly straightforward to program. It's not a long program. It works pretty efficiently. We fooled around with this. And this technique generalizes. I won't spell out the details because they're lengthy, but because this is working with sections of line bundles, it's actually quite straightforward to go and do this with sections of vector bundles, find approximate Hermitian-Yang-Mills metrics which satisfy a matrix generalization of this, and work out the moduli space metric. And this is about to appear in a simple example. Could be pushed through for quasi-realistic models. Again, one's getting an approximate Hler potential, but it's quite doable. One can improve the scheme. Okay, so now where did this thing come from, this complicated equation? I seem to pull out of a hat. And there is a kind of a nice physical explanation. I haven't quite figured out where this fits in string theory, but I believe it may. So whenever you talk about these sections of, holomorphic sections of line bundles, as a physicist, you probably should think wave functions in the lowest Landau level. That's the basic physical translation, as many of you will know. You can do a complex gauge transformation and turn these wave functions into holomorphic sections. Okay, so now I'm going to ask the question. Suppose we have a charged particle, a magnetic field on our calabi-Yau, which is proportional to a Hler form. Don't ask me why, but there are reasons to say that. And now we're going to consider this particle as a quantum particle, as a finite number of states in this lowest Landau level. What would it mean to say that we have the maximal entropy state of such a particle? Okay, well, it's actually quite clear for a quantum system of n states. You take the maximally entropic density matrix rho. Okay, so that's perfectly good definition. But given that it's a particle with a position, there is a second candidate definition you could propose, which is that you compute the probability to find it at a point z in position space, and that a priori is a function. But if it's maximal entropy, should not that be constant? That would be the maximal entropy probability distribution on the calabi-Yau. Okay, so we have these two candidate definitions of maximal entropy, and in general, they're incompatible. But it's not that they are directly incompatible, it's just very complicated given the magnetic field to calculate the wave functions and compute these things, and there's no particular reason that they should agree, but it turns out that exactly for the balanced metric, the magnetic field proportional to the Hler form of this balanced metric, the two agree. And that is, in fact, a physical definition of the balanced metric. And it's very easy to check it from the definitions. Again, it takes a little staring at these formulas to get your head around them, but it's very easy to see this, and it's proven mathematically that the balanced metric is the only one that does it. So to see that this actually well approximates Ricci flat as you take the K large, the magnetic field large, there's an expansion for the diagonal. In other words, the probability distribution, a semi-classical expansion, which was worked out by mathematicians, could be worked out using physical methods. We are trying to do that. And starts out constant, and the leading correction is the Ricci scalar. So to the extent that the balanced metric makes this constant, it sets this equal to this, and as K becomes large, it forces the Ricci scalar to 0. And so that's why. Okay, so then you can play with this in numerical examples, check the convergence, verify these statements. This is an example for small k of this is our first trial metric, the original metric on P4, restricted to an S2 in the calabi-Yau. It's supposed to be, actually I'm not restricting the metric, I'm restricting the deviation from Ricci flatness. So this will be perfectly round for a Ricci flat metric. And if you know, this is the ratio between omega cube, little omega cube, and big omega wedge, big omega bar. So k equals 1 is not very good. This quantifies my previous statement. As k increases, it gets pretty good. And so that's the type of check you can make. And again, so far it's still recreational mathematics, but I think it's a fairly tractable framework in which one can make statements about a preferred approximation to the Ritchie-flat metric, which may well make interesting contact with string theory. So I'll stop there.
Thank you. Questions, please? Okay.
With the warped Hler metric, do you think that the volumes of moduli space will still be finite?
Well, it's not a well-posed problem because the warp factor depends on other sources. So in a given string compactification, you know the branes and the fluxes and the other sources, and then you can ask it. But I don't think we have a sufficiently general description of that full problem to really study that question. Of course, I would believe it based on, you have general reasons to conjecture it, I have general reasons to conjecture it, there are other reasons. So I would certainly believe it, but I would not say I know how to work on the question yet.
More questions, please? Okay, please.
Do you think you can, with the corrections from the warp factor to the Hler potential, use this to uplift backward to the zero space?
In principle, maybe, because the potential really depends in this essential way on, it's got the inverse metric sitting in the first term. So by varying that in an arbitrary way, yes, you could push something from negative to positive potential, in principle. Yeah.
Some questions? If there is no questions, maybe I will ask you a more mathematical question.
Yeah.
In what topology it is more natural to describe a deviations of your balance metric from Ritchie-flat?
Yeah, that's a good question. I mean, it actually converges uniformly. They show that, so you can put a uniform bound on the convergence. So it's pretty strong. Yeah.
Mm-hmm. Okay, maybe. If no, let's thank the speaker again.